In this video, I'm going to talk about why matrix is useful. Since we talk about matrix and matrix operations, and one thing you might want to ask, why do we start a matrix? Okay, so here I'm going to give you a very simple example showing how we may use matrix to solve some important problems. Okay. All right. So the problem given you is example given you is called UAV formation flying. So this is a pretty simple problem. The problem is if I have multiple unmanned aircraft, air vehicles, I call it UAVs, and the goal is for them to align their heading. So assuming they're starting with different initial headings. So the goal is to make sure, for example, for two UAVs, I want to make sure that they are heading to the same direction. For example, I want them eventually they're going to flying towards the same direction. So they keep formation, which means their distance will be unchanged, assuming the velocity are the same. Okay. So if I denote the angle of the first UAV with respect to, let's say this is x-axis, this is y-axis, this is x or y, this is x or y plane. The angle is represented by x1, and the angle of the second UAV's heading with respect to the x-axis is called x2. So I can say the objective is to make sure that x1t minus x2t goes to 0, which means they will eventually fly in a formation, assuming they have the same velocity. Okay. So here we also assume that each UAV can mirror its current heading. Okay, can know its heading. For example, if it's turning, it knows its current heading. And also each UAV can communicate with the other one to obtain the accurate heading of its neighbor. So they're sort of as a neighbor because UAV 1 talks to UAV 2. They're sort of neighbors. Okay. We assume that UAV 1 knows its own heading and also knows the heading of UAV 2. Similarly, we assume that UAV 2 knows its current heading as well as X1. Okay, that's kind of assumption. Okay, so the action for UAV 1 and UAV 2 is to adjust the heading, because UAV 1 and UAV 2 should adjust the heading so that they will align the heading. That's kind of the goal. Okay, so assuming that we can change the heading, we cannot directly change the heading. For example, if I cannot change the direct UAV heading from X1 to X2, otherwise it will be down, right? I can only change the rate at certain velocity. For example, I can change x1 slowly, let's say either this direction or this direction, okay, at a certain rate, which is what I call x1 dot t, rate of change. So a typical idea, okay, I'm not talking about the algorithm side, but the algorithm we're talking about for this action is a simple one. Is just x1 dot t is x2 minus x1. In other words, UAV 1, if UAV try to increase or decrease the heading to match UAV 2. For example, if x2 is greater than x1, so in this case it is, because x2 is greater than x1, so x1 should increase its heading. So which means, hey, my x1 dot t according to this is positive because 2t is greater than x1t. So this is positive, which means x1 should increase. Yes, indeed, if you see I want to align the heading, this guy should go this direction, increase the heading. So it's help the synchronization of the heading. So if x1t is less than x2t, for example, it should decrease, which kind of similar, which is kind of straightforward. For x2t, it does the same thing. The difference is to be x2t dot t is x1t minus x2t. So it's very similar behavior as x1t. Okay. So we want to say, hey, can we, if we use this kind of algorithm or take this action for the two aircrafts, can we guarantee that this eventually the angle will be the same? Okay. All right, we have to analyze the solution, right? So we can write down, since we already know how x1t, x2 will change, meaning that how the two aircraft will change its heading. Okay. So we can have x1 dot t is equal to x2 is equal to x2 minus x2t minus x1t, as x1 s2t is equal to x1t minus x2t. Okay. Now I'm going to say, hey, I can sort of try to write this in a matrix equation, which is x dot t. Of course, xt is x1t, x2t. So x dot t is equal to, right hand side is just negative 1, 1, 1, negative 1 times x1, x2. If you write this in a matrix form, okay, and then you can write this as a. If I write this as a and this is x, okay, so I have x dot t is axt. Okay, so we can analyze the you want to find a solution. We have to find the eigenvalue and eigenvector, right? We can solve the ODE using the matrix diagonalization. We can find solution x1t, x1t, x2t to see if they will equal, right? Eventually. All right. So if we do the calculation, I don't want to talk about solution, but here if you do the calculation, you actually can see, yeah, x1t minus 2t will go to 0 eventually in this case. Okay, so which means the matrix A plays an important role because that's the only thing we can change is matrix A. The other one is just the state, right, of the matrix of the two aircraft. Okay, so eventually matrix A plays a very important role to determine if formation flying can be achievable. In other words, if the heading angles can be synchronized. Okay, so if you think this is pretty simple, yeah, I can see the roughly over there. What if I have multiple aircraft? So let's say I have not just UAV 1, I have UAV 1, UAV 2, I also have UAV 3, and UAV 4, okay? And also assume that, yeah, that they cannot talk to each other. For example, UAV 1 may only get information from UAV 2, okay? May not get information from UAV 3, it's really far away, cannot get information from UAV 4. And UAV 2 maybe can get information from UAV 3, maybe also get information from UAV 1, okay? And UAV 3 can get information from UAV 4 and UAV 2, okay? And UAV 4 can only get information from UAV 3, for example. So in this case, what would happen? Can we say they still can synchronize the heading eventually? So for a large number of UAVs, checking the eigenvalue eigenvalue A, because you can still write it in the same form, assuming you follow the same idea, okay? When you have more neighbors, it will be more complicated, of course. For example, if I represent this as heading angle x1, this is this x1 angle. Okay, let's say this is this is the angle is x1. This is x2. This is x3. This is x4 because x4 here is negative, basically, right? So I can still write this in action as x1 dot t is x2t minus x1t, and I can write x2 dot t. It's a little bit complicated because it has two neighbors to talk with. So I have x1t minus x2t. This is the first neighbor, right? X1. The second one is plus x3t minus 2t. And x3 dot t, x3t also has two neighbors. One is x2, one is x4. So I have x2t minus x3t and plus x4t minus x3t. Okay, and x4 will be x3t minus x4t because x4, the UAV4 only has one neighbor. So we have, this is complicated, a very complicated scenario. So one have we can write this and make sure for x1t, x2t, x3t, x4t. Okay, this is derivative, right? This is left hand side. If you write left hand side as this, then this is a big matrix times x1t, x2t, x3t, and x4t. Okay, so this is 4x4 matrix. I don't want to put in the number, you can put in the number. So this is very complex right up here. So we can analyze. We don't have to compute all the solutions exactly, but we only need to look at this matrix eigenvalues of A. So the eigenvalues of A plays an important role. So in later analysis, in some research, we'll see the eigenvalues plays more important role to determine if formation flying can be reached or not. In other words, we don't necessarily have to compute a solution, but just looking at the eigenvalue. That's why the eigenvalues, the matrix of the eigenvalues of the matrix, and in general the matrix property can be very important in some of the engineering problems.